I'll give people just a minute to get logged in on Zoom, and people here in the room to get settled, grab some donuts in the back corner of the room, and then go ahead and get started shortly. All right. Hey everyone, joining on Zoom and also those in the room, welcome to our first Data and Donuts event of the spring 2024 semester. My name's Alex. I am the GIS and Geospatial Data Coordinator here with the UT Libraries. Today, I'm going to be talking about open source data visualization and analysis with R. And this is also a co-branded event with the UT Open Source Program Office, shorten it to UT-OSPO, and I will get into that in a little bit, what that is and why this talk is co-branded with that. But thanks to everyone for attending. There are donuts in the back for those in person, and so those joining us via Zoom in the future, when we have in-person events, know that if you come into our beautiful new Scholars Lab, you can enjoy donuts while joining us in person. But before we get started here, I just want to share a welcome and a few workshop logistics. I will say for the people in attendance in person, we are on room mics that would be picked up on Zoom. So if you're chatting amongst yourselves, there's a good chance that people will be able to hear it on Zoom. So if you want to say rude things about me, or whatever, maybe keep that for afterwards. You just make sure to really be quiet about it, maybe text or something. So yeah, keep that in mind. I think feel free to to chomp away though on your donuts. I don't think it'll pick up those sort of small nuances. But yeah, so we are recording on Zoom. Everything will be available later. The slides, the script, the Zoom recording. So if I go fast over something, if there's something you missed, you can go back and reference that. You can also share it with friends, colleagues, things like that. And we will have a live automated transcription, but that's the Zoom transcription. Those aren't always perfect, so apologies if the quality of that is lacking. And then feel free to ask questions as we go. I sort of see this as an informal peer-to-peer workshop. So, if there's something I can help clarify, feel free to ask. Oftentimes with the scripting specificities, I may answer with something like, oh, well, have to, check the reference documentation or Google Stack Exchange. But, I'll do the best I can to, add any clarity or provide whatever I have. And then we'll run today until 1 p.m. Then I'll stop, and there'll be time, 15 minutes for any sort of questions. So anything I present on, any questions about maybe how your own data could be used in similar methods to what I'm sharing about today. There'll be time for that, and that goes for people in Zoom and in person. And then so the recorded workshops, lecture slides, and the code will all be available online shortly following today's presentation. So as I mentioned, this is the first Data and Donuts workshop of the spring 2024 semester. We have a really exciting lineup. And so as you can see on this little list here, the events with the donuts next to them, that means they're in person, where you can come and eat donuts. So we have one more of those coming up on February 16th. That's going to be research data management best practices, and that's during I Love Data Week, which happens to coincide with Valentine's Day. So it should be a nice, maybe romantic experience working with data that day. And then our last workshop is going to be March 1st, and that's discovering and utilizing data from research databases. And so the February 16th event is going to be led by Mike Wolshinsky, and then Meryl Grodsky is going to be leading that on March 1st. So if you're tired of hearing me talking after today's workshop, don't worry, you'll get some different faces and voices for those workshops. And as I mentioned previously, this event today is co-sponsored by the UT Austin Open Source Program Office. And so this is a new Sloan Grant funded office that started this year, well, in 2023. But what we do is we offer assistance across it's called the open source participation pathway. So, you may be familiar with open source software as, oh, great, it's free. I can download it easily. I can see the back end. I can understand it well. But, the open source pathway is larger than that, where we want to encourage people to not just use this open source software, but also start contributing to it. So, as you work your research and you notice, oh, I can improve this code this way. And maybe this customization I made could be useful for a lot of people doing similar stuff. But we want to help you along the way, to be able to sort of share those with the world. And ultimately, this sort of pathway is about broadening the reach of your research and making it reproducible, where you're able to share it with people, and they are able to reproduce your results. You're able to sort of move your research forward through that. And so, anything from today, we're sort of level 1, right? This is an introduction to an open source software. So that's that using, but hopefully as you start to use and, do get into that sort of customization, making different sort of advancements, you can get further along on that pathway. And so we are here to offer support in a number of different avenues for anything related to that. All right, well, so the open source program office, and I sort of got at this, but why open source? Why is it important? Why is it a focus of this R workshop? Well, open source is great because, you can download and access software free of charge. That's awesome, right? And when you leave the university, you don't have to worry about university-specific licenses. You don't have to worry about proprietary software, changing things, making things more expensive. And then, users can contribute to their fields, their communities, and so you can ultimately, produce this reproducible research that, reproducibility is fundamental to the scientific method, right? All right, so now that we have that established, and keep that in the back of your mind as we're delving into R, that one of the great things about constructing these workflows is that they're reproducible on your machine, but they're also reproducible for other people, collaborators, anyone interested in research. So I'm going to introduce R, which is a powerful open source statistical computing and graphics software. For my curiosity, for those in the room, who has experience with R? Okay, great. And who would consider themselves pretty proficient with R? Okay, someone. Good. I mean, that's what I kind of hope for an introduction to our workshop. So, and I would imagine we have a variation of experience levels for people on Zoom. But my hope is that whether or not you've even really considered R before, should be hopefully get something out of this workshop. So we'll start by looking at some basics about objects, operators, and functions, and then we'll actually go through an example research workflow. We'll see how long or how far we get through that workflow in an hour, but it should be pretty interesting. I think we'll be working with kind of a little data set. So getting started, if you don't have R software installed on your computer, That's okay, you don't need it for today, because I have the script linked in a Google Colab environment, so you'll be able to access that and follow along whether or not you have our software installed. I also, in that same link that I'll share in just a little bit, and is also shared in the Zoom chat, you can access the RMD file, which will run on like RStudio, or if you have R installed, or a different coding interface of your choice that runs R. But to get started here, so R, you can go download the R software package, which the logo looks like this. If you just search R download, you should be able to find it pretty easily. And then you can run that right out of the box. It comes with its own command line that you can run our functions on it just fine. But most people like to use RStudio along with that, which is an interface that allows you to visualize plots really effectively. You have different options for producing notebooks and shareable documents that integrate your code. So I do recommend downloading RStudio as well. I think it's a really nice, fairly approachable user interface. All right, so out of curiosity, are there people who are pretty proficient in other software languages here? So anyone like a big Python user? Okay, cool. So and I imagine people on Zoom, we have some Python people as well. Well, so why R? R is, it can do a lot of things, but one of its primary focuses is for data analytics and visualization. And so I think that for those purposes, R is really smooth, it's pretty approachable. And so I think, compared to something like Python, R probably doesn't have sort of the same breadth in terms of things you can do. But if you're really focused on data analytics and visualization, R can be pretty great. And I think, some people think that the sort of data analytics and visualization in R is preferable to sort of those in other languages. And then another reason, so I would imagine, a lot of people here, most people are involved in academic research of some kind. So, R is really popular for that. I think those dynamics are always kind of changing, and I know Python is probably gaining more and more popularity. But traditionally, R is really popular in academia. So there are a lot of statistics textbooks that are based in R. A lot of publications that come out with R code attached, specific R functions. So if you have the ability to script in R, you can really stay on the cutting edge with that kind of stuff. And so, and then again, open source, which I've already focused on. You can share your code widely with collaborators. And ultimately the choice between, do I want to learn R, do I want to learn Python? It's really up to you. What do you prefer? What do your collaborators in your lab use? Things like that. So, and it's one of those things where once you learn one, the other becomes easier to learn. So, and if you can use both, I think that's a big bonus too. All right, so one of the things with R, and if you're familiar with some other scripting languages, you'll be familiar with this, is that there are packages that offer extra abilities that just don't come natively with the software that you can install and run and are constantly being developed and added to. And so, I'm not going to introduce a lot of different packages today, and part of the reason why is because on the Google Colab, when you're running R on there, it takes a long time to install external packages. And so that's one reason we're keeping it simple. But another reason is that ggplot2, which comes within the tidyverse package, which is this large package of a lot of really useful functional data analytics methods. It is really powerful, and one of the sort of primary uses that I think people who really like to use R gravitate towards is ggplot2. And so GG stands for grammatical something to approach plotting. And so what that basically means is that it is a plotting software, a visualization package that is built to be really sort of approachable and to just have sort of a language and syntax that makes sense to people. So that comes in this big tidyverse package, which has all this different functionality and is sort of made to work all together. So if you have data that is sort of able to work and that is formatted within the tidyverse format, then it should work pretty seamlessly across these different packages. So a few of them, you have ggplot2, which I mentioned, tidyr, which helps you tidy up your data to work in the tidyverse format, and then things like dplyr, which is good for data manipulation, and then knitter, which helps you sort of broadcast your script and share it widely and make sure that it works while you share it. And so now, just before we get started actually diving into the script, I just wanted to go over some really basic syntax. So let's see, we have first install packages. So that's going to be really useful when you have your own specific research questions that you're looking to answer. There's likely a package that may speak really specifically to those methods that you need to use. And so you would use that install package function. And then the one thing to note that when you install a package, you have to use quotes around it. It can be either single or double quotes. And then once you install it, you can notice when you load that package using this library function, yet you don't need to use quotes anymore. But so that's as simple as it comes for installing a package. Just install packages and name whatever package you want to install, right? And you can look up packages either in RStudio has an interface for looking those up, but you can also Google your specific method that you're looking for and R package, and you should be able to see if a package that's relevant to you exists. All right, and so then a really sort of basic useful thing to know in R is how to establish a variable or an object. So here, if you're familiar with Python, right, you use an equals sign to do something similar. In R, it's this less than sign and then a dash. And it can get pretty annoying at first if you're used to just one key, like an equals sign, to establish variables, but you get used to it pretty quick, the less than arrow. And so you, in this case, and you're usually maybe performing some kind of function. In this case, this example, the function is read CSV, where I'm reading a CSV file with the name of my CSV file in those parentheses. And then I'm going to call that CSV data that's going to be stored as a database in R. I'm naming that uni. I could name it whatever I want, as long as it meets some certain basic criteria of what you can name a variable. And then lastly, so functions, R is really built on functions. So as I said, like this install packages, library, read CSV, those are all functions. And the way that functions are denoted in R is that whatever sort of parameters involved are within the parentheses. So here, right, the parameters for install packages is a package name, ggplot2. And then in this, read CSV, the parameters are my CSV file I want to use. And then, so when you're writing your own function, then the function is actually stored within these curly brackets. And so this little slide thing is showing up, there it goes. You can see at the end, there's a curly bracket that denotes, okay, that's what the function is actually doing. And those parameters are in the parentheses. And I also wanted to share, so there's a standard sort of package documentation format in R that you can access online for any R package. And it looks like this, and it describes all the different functions and the parameters involved in those functions and all the different options that you have to work within those packages. So that's a really valuable reference to use when using any package or those official documentations. All right, so let's now get started with the actual scripting. So this is a workshop, right? So we'll get to it. So you can go ahead. It's linked in Zoom for those online. For those in person, you can go ahead and type that bit.ly link into your URL, and you should access a list that's going to link to the slides themselves, link to a Google Colab environment that's posting the R script, and then you can also link to a box link that will allow you to download the RMD file for using in R software. Yeah, did everyone get a chance to type that in here?
I want to get up.
You got a picture? Yeah. Okay, awesome. All right, so that Google Colab link, you may have to log on with your UT account or a Google account to access this. But this is what that looks like, and you may be familiar, especially if you're used to working with Python, maybe in a collaborative environment using Colab. But what it allows you to do is host a script and run it on the Google platform. And so if it's primarily used for Python, as I mentioned, but if you want to run it for R, what you go here is change runtime type. And here you can see I have it set as R, but here's the dropdown. You have Python 3, which is the default runtime type. So if you just get on a blank Google Colab, you press new Colab, it's going to default to Python 3. So if you start writing R syntax, it's not going to work until you switch it over to R, but then it's easy as that. So feel free then to make a copy of this, so then any sort of changes you make as we go along here, you'll be able to save those changes for yourself. But that's what this looks like. And so feel free to run each one of these scripts. So the script are in these gray boxes, and then the text you can see is above here. You just press that run button. But I'm going to switch over now to my R notebook within RStudio, just because this is probably, if you start to use R, what you will likely use more than a Google Colab environment. So I wanted to give this sort of as an example here. And then, so the text size, how is that for people maybe in person? I think people on Zoom can probably likely see that, but for those in the back, is that too small? Small. Looks good. Okay, then I will keep it how it is. All right, so let's start now by just defining a simple object. So one of the simplest things we can do is just create a numeric vector. And so as you can see, we're using this arrow sign here to denote, okay, we're creating an object, which is, it's named X. I could name it pretty much whatever I want. And then I'm denoting a list of different numbers here separated by commas. And so when I run this, you can see nothing's really going to happen because I'm just establishing an object. But now if I go down here and I use the print function, you can see here it prints out my my numeric vector. So those different numbers. And you can go ahead and see here, I can rename this to like 1, and then if I run this again, you'll see it'll still run, because notice, and this is, you can visualize this a little bit better in RStudio, I still have this vector stored here as X, but notice now I have basically the same vector that just has a different name. Also notice, so if I want to print a variable and I make a mistake where I have a capital O where I didn't name it capital, I'm going to get an error because capitalization matters with those names. So keep that in mind, pay attention to the capitalization. change that back. And so one thing you're not allowed to do is name it like a number. So 1, it'll probably throw an error for me here. But I can, if I want to call it 1, probably let you do that, but I kind of try to keep the numbers out of my object names, but it's up to you essentially. So I'll just bring that back to text. And then here you'll notice, so that print simply with our object in the parentheses just prints out our vector, right? So we see those numbers. But then what's going on in line 16 here with our square brackets with 2 in there is that the square brackets are basically used to parse through a data set to find some specific data points. And so in this case, what we're doing is we're parsing it to find the second value. So 2 is going to bring up 5.6. If I change this to 5, it'll bring up the 5th order in there, 21.7. So we'll use those square brackets to do some more powerful things when we start working with a larger data set in a minute. And then we can get a simple summary of our numbers, right? So this summary function is just built into R, and you can see we get, so our measures of central tendency, we get our different, our minimum and maximum, things like that. Now we can also check and see what type of object do we have by using this class function. You can see here, if I run this, it's numeric. Now, if I go back up, change one of these to, let's say, a name. I'll need to, if I run this now, I'm going to get an error because I didn't put quotations around the name. So if you're putting a name in a vector like this, quotations. So now I can run it. Happy with that. But so now let's see if the class has changed. You can see now it's instead of numeric because I changed one of those numbers to a character. And that can be useful. So class, if you're running some kind of function, you're getting an error message that says expects an array, expects a matrix, which are just different examples of different types of objects in R. Then you can go, oh, well, let me check and make sure that I am inputting the right type of object into this function. But yeah, so as I mentioned, so that the vector is a really simple object type. It's the basic one. There are matrices, there are arrays, that are used for if you're doing, matrix algebra, things like that. But I think one of the most common data types to work with in R are data frames, and so that's what I'm going to move on and focus on for this workshop. Our data frame. So a data frame is essentially like any kind of table, right, where you have rows and columns. That's essentially what a data frame is in R. And so here, so what we're doing is we're creating a data frame. And so you can see again, right, remember R, the functions happen inside these parentheses, or that's where the parameters for the functions go, are inside these parentheses. So using this data frame function to create a data frame. And so data frames, you can feed it different vectors. Like, so remember that very simple vector we were looking at before, that can then become a column in our data frame. And so I forgot to mention before with those vectors, so that's what the C function in R is doing, is it's creating a vector. So here we have a series of vectors that are then going to become our columns. So if I run this and print it, I can see what my data frame looks like. So it looks like a table, right, that you would see as a CSV or in Excel, right, where I have name, age, and vote. And so notice these are different types of vectors, right? So I have character, I have numeric, and then I have a Boolean, or it's logical, I think, in our language, where I have the Boolean true false statements. So are they a voting age for the 22-year-old? Yes, true. For the 15-year-old, false. For the 19-year-old, true. And so here we can take a look. So the class, right, of our data frame, obviously it's going to be data frame. And then, yeah, if we look at that vote, that is logical. So it's those Boolean true false statements. All right, and then I can do some simple visualizations here. So I can make a bar plot where I can look at our different people in our data set and see what their ages are. Pretty simple. So you can see, I think the syntax for that is for a bar plot, our inputs are height, and then names, which is going to be what we name our different categorical variable on the bottom. So, and then here you'll notice, I think this is the first time we've used this, this $sign here. That's going to denote within our data frame. So we define the data frame on the left side of the dollar symbol, and then we define the specific column we want to work with on the right side of that dollar symbol. So you can see, so say, okay, we want to work within our data frame 1, and I want to work with the age column, and then same thing here, still data frame 1, but then I want to work with the name column. I can also use some of that parsing, right, that we introduced before with those square brackets to select certain data I want to select. So here I just want to keep the people who can vote in my data frame. So I'm using this language, so data frame here, and then the column I want to select is vote. And so remember, on the left side of the $sign, my data frame, on the right side, the column, so vote. And that's that Boolean true false. So I just want to keep those people that can vote for true. And notice, so there are two equal signs here, which basically saying is, like, I want, to keep people who can vote or, are equal to that true. And then with numeric variables, I can use like greater than or less than. So here I want to just keep the people who are under 20. So I'm using the less than symbol there. Now you can see what these different data frames look like. So here is my under 21, and here is my can vote data frame. And one thing that I want to point out here is it looks like I have a typo in these, right? That I was going to put something after these. I put a comma so I could, write something else, and I forgot. Now that comma is actually really important, because what it's doing is a comma on the right side there within our square brackets is going to say, I want to subset those specific rows that I've identified. So if I take these commas away, it'll probably run. But it's not going to actually subset those rows. So I'll probably just get, the same data frames there. And that's something I may, if I am doing an example later and am using the square brackets to subset, I very likely may forget to put the comma in there. That happens to me all the time. And that's just one of those things where, look, I don't think it makes a whole lot of logical, sort of sense for if you're not familiar with the R language to explain why the comma being there explains to subset the rows, but that's just one of the things that you kind of have to, memorize and learn as you're learning a language like R. So those little nuances like those commas are important, and one of the ways that you learn that is either go on a Stack Exchange kind of thing, the R documentation, or just learn by fiddling around and doing some troubleshooting and you get an error. All right, now we have just sort of that simple kind of basics that we went through, and we could do a lot more. We could go into like the different arrays and matrices and stuff like that, but I want to get into working with some functions and then get a real data set in here and do a few things with that. So here are just some functions, really simple, but I think they sort of drive home the point of how they work. So here in this first one, we have a function that we've named circumference. So, right, and for those of you who might forget their geometry class in high school, that's a 2 pi times radius is how you get circumference. So that's what that is. And notice pi, R recognizes that as a number. So we only have one parameter in here, and that's R. And you can see we define that parameter up at the top here. And so we just have one input, and when we go to run the function, so I'm running it within a print statement so that it comes back with a number for our circumference measurement. So we put in 8 as our radius measurement, and then that's going to put it in the function as our variable that you can see is here. So I can run that, and I can see what's the circumference if I have a radius of 8, and obviously it's whatever sort of metric you want to imagine. So I can change that to 2, right, and I'll get a different value. So another thing you can do is you can have a default value for functions. So say, for some reason I want the default value here to be 2, then I don't need to put any parameter in here, and it'll just run with that default value. But even if you have a default value in there, you can still supersede that. So if I put 5 as an input, it'll change that. So just something to keep in mind. And when you're working with functions, that's something to pay attention to, is they'll often have a whole list of different parameters that you can change if you want, but they just come with default values that they run with. So, if you're running some complicated statistical function, there's likely all kinds of different parameters that you can mess around with if you want and customize, but they come with just default values that they run with. So something to keep in mind there. All right, and so this next one is a slightly more complicated example, which is a function to roll a dice. So here, right, we have our function defined, and notice there's no input parameter. So you don't have to have any kind of input parameter if you don't want to. So this is just a fully functional function with no input parameter. But you can see here, you can change these. So we have our die, which is just 1 to 6, a regular 6-sided die. And then this sample function, so we have a function within a function, which sample is going to just randomly select integers from our number list. So that integer aspect is important with sample, right? Because if it was sampling, 2.7, that wouldn't actually reflect, right, rolling dice. But in this case it does, and then we just sum up, right, our dice. And so I can press this and it'll roll, and I rolled a 7. I can roll again, 2, 4, you get the idea. I can make like a Dungeons and Dragons style, like, complicated dice with 30 faces on it, and I can see how that changes. And then one thing I can do is I can use this replicate function, to run that function 100 times and see what the mean of my rolls are. So if I have a 30-sided die, well, yeah, and then the dice, it comes around what you would expect, somewhere in the middle, 31.51. If I change this back to a normal dice, and then run this again, notice now, yeah, it's that sort of right in the middle there. I can, if I want to get a higher sample size, I can change that. It still runs pretty fast. I put a whole bunch of zeros on Google Colab a few nights ago testing this, and I did crash the RAM at like some crazy like 1 billion number. So you can't get carried away with that. But now let's get into working with a real data set, and we'll do some more complex visualization kind of stuff. And if we get to it, we'll run a little multiple regression analysis. But if we don't get to that, you can run it on your own. You have the script. So here, I'm just making sure I have that tidyverse library loaded, and it should come with your Google Colab R environment, so should be able to run that just fine. If for some reason it doesn't recognize that, you may have to run that install packages command and install tidyverse, which may take a little while. But now let's use that read CSV function that I gave us an example in the intro slides to bring in a database here. So these data I found available through GitHub are from university rankings. I think that the Times Higher Education, which is one of the sort of prominent university rankings, I think those are always interesting to look at. What I like about this data set is it has different variables associated with ultimate scores and rankings there. So we can actually sort of unpack and try to understand how the model works in terms of the variable importance for coming up with the institution scores and rankings here. So we can take a look at what this looks like. So here, right, our data frame is a lot more complicated, right, because we have all these different variables. So we have rank, and this has a bunch of different international universities. So I think ordering them up to almost 2,000. And then we have it for, you'll notice, different years. You can find the year column here. So we have the rankings from 2016 through 2024. And then we have these different variables that they may input. So like teaching scores, research environment, research quality. You can see all that information, you know, and see the quartile ranges, the measures of central tendency, the min max, just by doing this summary. And then we can look at our table itself by doing the head function. And so that just comes out with it. I think it defaults to just showing the first 6 rows. And so this is from, I think, the 2016 data. So you can see like California Institute of Technology was ranked first in 2016. And then you can see overall score rankings, things like that. So that's that head function allows you to preview your data table there. And notice, so in Colab, you don't get this, but on my RStudio environment, I can now take a look at my variable or my object I named uni, and I can see all those different columns within that easily here, and I can keep track of the objects I've established. So there's my uni. Now we can use what we learned with those simple data sets with our square brackets to, let's see where UT Austin ranks in there. And so you can see, pretty good for all those schools. These are international rankings, and have a nice high overall score. So you can see we're doing really well in 2024. Up to 75 and 72 in 2023. So I don't know if any of y'all have noticed differences around campus that warrant that big jump. I will say I was hired in 2023, so maybe a coincidence, may not be, I don't know. So we can take a look at how these variables interact with the overall score here. With a nice simple scatter plot, where this is research environment. So as far as I can tell, the research environment is like they track things like overall funding for research, like grant money, things like that. And then research quality is like mostly citation driven because there are those 2 separate research variables. You can see it seems to correlate pretty well with that overall score that we have on the y-axis, and on the x-axis we have that research environment score. And we can look at other variables. So like, that research quality, which is like tracked by citations, looks pretty similar. But maybe we want, these charts look fine, they don't look great. We can use ggplot to get more control over the aesthetics and add some different features. And so you may notice some of the aesthetics probably look similar to some publications you may be familiar with, because a lot of people use ggplot for publication ready figures. So here So that research quality data, so, and then here we've added a feature. And notice this, so this is how the ggplot syntax works. So the AES, it basically stands for static variable. That's inside you define like the X and Y. And notice it's a little bit different where we're not using that $, like denote the data table that way. Instead, we're denoting our data frame here as uni, and then from there in the AES, we're putting in our parameters of what we want on the x-axis and what we want on the y-axis. And here we use these plus in ggplot to sort of, okay, this is another argument I want to make, or this is another feature I want to add on to it. And so in this case, another argument I want to make is, you know, I want to specify that the way I want to make the data appear are points, right? So those are my geometry points, and then this geometry smooth is what adds a modeled trend to the chart. And so in this case, this is just a basic like linear regression trend. So that's what that LM stands for, linear model. And so you know you can select different methods. You know, if you have data that you know a different type of model would fit it better. But you can see here if I want to do some more customization. So, you know, there are a lot of data points in this data set and they kind of run together here. So I can simply change the point size here. Saying size, let me go down to like 0.5, see what that looks like. And so easy as that now, you know, I've made a little aesthetic choice, customization my data, and then changing the color is as easy. So I can say color, and notice I can, within the RStudio, it gives me little hints about what these different parameters are if I start to type them in. So here, color, and I want these to be green. And that's kind of a cool little feature of RStudio as well, because it assigns those colors. You can also use like hex codes if you want. If you have a really specific type of color, you can work with. So there you go. I mean, that's kind of an, you know, obnoxious green. So I probably would want to, you know, go on to my hex code and change it. But yeah, there you have it. And you know, for changing the color of the line, it would be the same thing, just going in here in the geometry smooth marking there. And so here we can see, you know, a data variable that's not as nicely distributed is, I think, what this is student to staff ratio here. Yeah, and so we clearly have some outliers, right? So this is a weird looking chart. Well, one thing I can do is I can use this argument here, which is, so notice here I'm doing something slightly different. Instead of just using that ggplot function and having it print out right away, I'm defining an object that is a ggplot object. So naming it G and running that. And then I'm going down here and using that plus notation, right, that ggplot uses to add another argument, which is I'm doing a limitation on the x-axis and limitation on a y-axis. So here, you know, this students to staff ratio, you can see a lot of these outliers here. I can't really tell what the actual, you know, majority of the data look like. So I'm putting a limitation on the x-axis here.
Alex, there's a question in chat.
Oh, okay. Look. Yeah, I'm fairly sure R does, and ggplot I think probably has their own specific color key list, so you could go ahead and look at that. I know certainly when you start working with like color ramps, things like that, to model continuous variables, or you know, color schemes to model different types of variables, those also have their own names and are all sort of stored within that. And you can also, you know, customize those as well with hex codes. So yeah. Good question. Yeah, so here you can see I applied those limits on the data. And as it plotted those, it's not just zooming in. You'll notice importantly, because it affects how our modeled trend line looks, it actually takes those data points away. So they're not influencing our line model anymore. And so you can see now we can actually visualize the majority of the data much better that way. And next, we can do things like color our points, say by year in this case. And so, yeah, my example of color ramp, this is yellow to black. You can see I'm just defining it myself. But again, yeah, as we had that question in Zoom, I think there are specific color schemes that are probably stored within ggplot, and then I know there are also extra libraries that you can access, such as Color Brewer is a really great one for working with aesthetic colors, where it has sort of suggested really nice color schemes according to color theory, and you can choose like colorblind safe options, things like that. So yeah, certainly you can get really granular with your aesthetic decision making and the colors and things you want to use. But here, what we're doing to make this these data appear by year is in here you can see we're adding an extra to geometry point, this AES, right? Because that's where we make our sort of main plot arguments within a ggplot. We're saying assign color according to year. And then here we're defining our scale color gradient and so on. And I took the time with this one to, you can see, produce a title and change make sure that the names on the axes are correct, things like that. If we want to sort of display that data in a different way, we can use faceting, which you can see this facet wrap argument down here. I just go by year. And so that's that little tilde year is saying facet according to the year. So now we can compare, okay, how did these trends look across 2016 to 2024? Since when we just colored it by year, that was kind of messy, hard to differentiate. So you really have, and this is skimming the surface of the options you have a ggplot to make aesthetic choices. And so, if say you were using Excel or something to create charts and you wanted to reproduce something like this for a publication, that would take a really long time, and then you'd get all these together and then you accidentally move one and all the alignment is off. So this makes it really easy for you to do that. And then, similarly, this is just doing it by, I think, country to give you an idea of, you can do it with a lot of data points too. We'll see that this one takes a little longer because we have a lot of countries in this data set. Let's see if that will run for us. And there you get an idea. Okay, we have probably too many countries to do this effectively. We have to go in and make some customizations to make this look nice. But you get an idea. It's really easy to produce a lot of data visualizations at once and make them in a nice way to compare them. But you do get an idea, so you can see like, the US has a lot of universities that show up in this list, United Kingdom, things like that. All right. So say we wanted to do a bit more customization and we wanted to compare two schools and see where they land on those scatter plots. So here I'm making two objects. So we have UT, and then I'm choosing Texas A&M as a nice little comparison. And then what I'm doing is running this regular chart so we can see the distribution of all the data and then visualize within that whole distribution our schools of interest that I'm then adding on those points later. Here you can see those two individual objects and assigning them their own colors. And so comparing research quality again to overall score, we can see UT versus Texas A&M in terms of the research quality score along the x-axis, and then that overall score on the y-axis. And so, I know that's the wrong orange color for UT. If you wanted to go into the brand book and get the hex code, and do that, you can do that, but I think the orange shows up there nicely. You can see, yeah, UT doing pretty well. And we can, I'll just finish with some last kind of more kind of data upkeep kind of things. So we can remove, or we can look for outliers using a box plot. I know it was these data sets with those scatter plots was pretty obvious, and with the like population where there's some university that has more than like 1.5 million students. I think it's in Turkey. But clearly a lot of outliers. So if we were doing like a multiple regression analysis, we wanted to remove those outliers. We can write a little function to do that, right? Where we're calculating quantiles, and we're specifying our 25%, 75% range of that, and then we're doing the standard deviations here times the interquartile range, which we're defining. We want that to be our student population here, and then creating a new object in which I've eliminated the outliers from that student population set. And now you can see the box plot looks a lot different, where the y-axis makes more sense with like 60,000. So now you can run that data without it being really influenced by outliers. But say we want to run that and remove outliers from a lot of our different columns all at once. We can do that here by writing a slightly more complicated function. But then we're going to write like a for loop where it goes through those different columns that we define and searches for outliers. So here I've just put 2 in there, so student population and student to staff ratio, because those are the ones we know have outliers. I can run that. It may print on Google Colab a really obnoxiously long list, so I apologize for that. You can see on RStudio it's a lot more manageable. And then we can just test and see if that worked by plotting our new object, which notice I've just named new. I was kind of lazy with that nomenclature, but now I can see, okay, yeah, we have our data set that have the outliers removed automatically. And so now using our new set, we could go through, and I'm going to look using this density plot type here to look at normalcy. So if I'm running say a regression analysis, I can look at normalcy, compare those different columns, see what that distribution looks like. And then lastly, so if you haven't really had an intro to regression in 2 minutes, I'm not going to be able to explain it well at all. But generally it gives you a way to sort of test how much certain variables influence your dependent variables. So in this case, let's skip down to the multiple regression here, which let's try to see what the most influential variables are for coming up with these sort of total scores for university rankings in this model. So in this case, I'm using my my new data set here that has had those outliers removed, and I am going to build my multiple regression. So here I'm doing this linear model. So we actually already ran this just within our scatter plots earlier, but here I can run a multiple regression, and now I can see those coefficients. I can see the intercept. And so those coefficients, they basically apply to how much they influence our dependent variable, so total score. And then you can see here, if we're just doing a simple sort of preliminary read of these, we have a pretty well-performing model, which means that of the variables we have, that seems to be the actual variables going into calculating the total score, because we have an R² of 0.999. These are all highly significant, which you would expect anyways with a data set this large. But you can see here, we can kind of assess that, all right, 30% of the total score is influenced by research quality, 30% influenced by teaching, and roughly the last 30% is research environment. So those seem to be sort of equally weighted within that final score, and then the other variables don't seem to have that high of an influence. Just an example of some other sort of regression outputs that you can use to sort of assess your model performance. And then here we can separate training and test data, so we can test the predictive power of our model. And I don't really have time to get into the specifics of that, but here we're basically separating 80% to train our model, and we're leaving 20% to then use as test data points, so we can see the predictive power. And then we can actually run our new model with just having our training data there and test it against the test data, and we can see what sort of accuracy we get using a confusion matrix. And as we would expect with our model that seems to be performing really, really well, we get super accurate predicted values according to that confusion matrix. So there you have it. I think it's 1 now, so I promised I would wrap it up here, stop talking so that we can have time for questions. But you can see, that's what goes into university rankings, and they do seem to actually be sharing all the important variables that go into that according to our model workflow here. But hopefully, you could see some of the advantages of producing a reproducible workflow using an open source software program like R. The great thing about this is I have it written, so I can just rerun it anytime I want. I can put a different data set into it, run it, and I should get sort of the same methodology, and if I'm running the same data set, I should get the same results. If I send it to someone else, they should get the same results too. So it's reproducible for me, but also for collaborators, and the methods, the software should be reproducible for a whole community of open source software users. So thanks very much for those in person and on Zoom. I'm sure there are probably some donuts left. So for those in person, make sure to grab some more donuts, and I'm here to answer any questions from people online, in person, and yeah, thanks for coming. Happy Friday.
Thank you.
Yeah.
Thank you so much for this. I just wanted to ask about data frames. It sounded to me like most of what we're doing here can kind of be like, it's basically equivalent to two-dimensional. I'm wondering if there is ways to increase dimensionality to plot 3D or 4D, 5D data and store it.
Yes, I'm fairly certain there is. I'm not gonna lie, I don't have very much experience working with three-dimensional arrays, things like that in R, but it does definitely have that functionality in it, and I think really sort of specific programs that you should look into to see.
So the data frames format itself, it doesn't really have any restrictions or limitations on dimensionality.
I'm not sure if the data frame format specifically can integrate. You may have to work sort of more in like a three-dimensional array, format. But yeah, that's definitely something to look into. And yeah, I don't have experience, but I've definitely seen sort of ggplot produce like really cool, sort of three-dimensional feature space plots. So I'm fairly certain it has that functionality. But yeah, again, probably worth looking into. If R or Python probably has comparable functionality, so people may say, oh, well, Python's not better for that. But yeah.
I work a lot in R, and I work with like really large data sets, and I was wondering if you've ever run into this. Every once in a while we like R updates, and then we have to update all of our packages and everything. And then sometimes we don't want to because we have to go through and see, oh, how is it going to treat the data differently? Do you have any suggestions on how to like do with that? Because we want to be able to keep all of our previous data reproducible, but we don't want to fall behind computationally.
Right, and that is a really good point, is that reproducibility, in theory, it should always be reproducible when you come up with a workflow like this, but there is that thing, oh, I open it 2 years later and all these packages are deprecated and work differently. So yeah, I mean, I've certainly experienced that with recently I work a lot with geospatial data, and some of the key geospatial data packages had some pretty significant changes. But that's where, so things like if you're working with like GitHub, where you can either use the enterprise GitHub at UT to share within UT collaborators, or a more public GitHub. Then you can sort of track your different versions, and if you're sort of making those changes and adding, you can document those, and so users can kind of see how, why those changes were made. And again, that doesn't really solve that problem of having to make those changes, but it definitely at least makes it so it's documented and sort of adds to kind of the the open reproducibility aspect to it.
Yeah, so this is also because like we're a biology lab who had like probably not a lot of like formal training in computational methods.
Yeah.
So like we use GitHub a little bit, but do you recommend like using it primarily for backups, because we just have everything in like work or scratch folders like on a pod server, but so
Yeah,
it's kind of
I
hard
think
to go through.
yeah, I think it's great for backups. It's especially great. So Michael and I have been producing a lot of like Python code now for our geodata portal.
Mm-hmm.
And so we're kind of working independently on some different scripts, and then we push them together onto a GitHub repository, and make updates. And so we can view all of our sort of revisions there and all of our different versions. So yeah, I think as backup, but then also as a collaborative space, and updating different versions, keeping that all documented. GitHub is great. And yeah, for any questions about GitHub usage, the UT OSPO, the Open Source Program Office, that's one of our sort of major focuses. So if you have any questions about that, reach out to, you can find the UT OSPO website. It's, just Google UT OSPO and find our contact information on there. Yeah.
I have a question about RStudio versus the collab. So
Yeah.
we're working locally. Would you suggest RStudio rather than collab?
Yeah, I really like RStudio. I like that. I mean, I didn't really show this, but you can see like if I just, because I was using like a notebook here where I have it similar to like the Colab where I have the code chunks, but just like a normal R format, it will print outputs as like plots here. So let's see if I run this. Yeah, I get that. So it I think just offers a really nice kind of dynamic interface for visualizing your plots, for keeping track of all your different objects up here in the environment. And you can see sort of how things are running down here and all the specific error messages and stuff like that. So I really like RStudio. I think it's a really sort of efficient and approachable way to use R scripting. But I think some people, if you're used to command line scripting and just want to use the baseline R software and use a command prompt to run it, you can be lightweight and use that as well. So
Is there any difference in processing power?
no, I think it should have the same processing power because it's still running background on the R program itself. I mean, I think the processing power is a lot greater on the locally using it versus Colab, because the Google Colab, I think at some amount of RAM, I think it's like 12 point something, it just cuts out and resets your whole runtime. So yeah, but if you're running it locally, R versus RStudio, I think it's pretty much the same computing power.
Alex, there's two questions on
Okay.
the chat as well.
Perfect.
Yeah, that's the first one.
Okay. Yeah, I think so. For that question, I'm not totally sure. Really, my experience with using an IDE for R ends at RStudio. I've been using VS Code, I know, for Python lately, and I'm pretty sure that has compatibility with R. So there certainly are a lot of options out there. I'm not familiar with any that are specifically sort of intended for really large data sets or things like that. But I'm sure those probably exist. And, I would say along with IDEs, certainly different packages are adept and meant for, handling large data sets, working with like 3-dimensional arrays, things like that. And then, yeah, I think that goes with, things used outside of academia, certainly. I think there are like specific, industry targeted, libraries and things like that. So. And then. Yeah, great. I think that's a really good idea that's in the chat as well, which is, a workshop on, troubleshooting errors in programs. So we'll definitely keep that in mind for future planning of data and donut workshops and also different types of workshops. So thanks for the suggestion. Okay, well, if there aren't any more questions in person or online, everyone have a good rest of your Friday. And yeah, again, for people in person, grab some food on your way out. And also, I'll stick around here for next few minutes if you want to come chat about anything specific. So feel free to hang out in this beautiful data lab. I don't know if there's anything happening right after this. To utilize this space, but thanks everyone. Have a good weekend.
Thank you.
Thank you.